Hello, my name's Gabe. For this problem, we're given the vector valued function f is equal to negative y plus zi plus x minus zj plus x minus y k. And we're given the surface given by z is equal to 9 minus x squared minus y squared, where z is greater than 0. And we're asked to verify Stokes' theorem by calculating this integral two different ways. So one way, using Stokes' theorem, the double integral, and then we're going to use what we know about line integrals to evaluate using a single integral. So let's go ahead and let's get started by trying to find what this integral is using Stokes' theorem. So the first thing I'm going to want to do is I'm going to want to find the curl of f. So I'm going to come down here and start working towards finding the curl of f. So here, you'll want to remember that the curl of f is this, whose top row is given by I, j, k. The second row is going to be the partial derivative with respect to x. We'll have the partial derivative with respect to y, and the partial derivative with respect to z. And now the third row is going to come from f. So we're multiplying negative y plus z by I. So negative y plus z will be in the first column, third row. Coming over, we'll have x minus z. And coming over again, we'll have x minus y. So now we just need to compute this. So if we're trying to find what we want to multiply I by, well, it's going to be the partial derivative of x minus y with respect to y, which in this case is going to be negative 1. And we're going to be subtracting the partial derivative of x minus z with respect to z, which is going to be negative 1. I'll multiply that by I. Next, we're going to subtract. So for our j part, we'll have the partial derivative of x minus y with respect to x. So in this case, that's 1, minus the partial derivative of y minus z with respect to z. So that also is going to be minus 1. And finally, for k, we're going to have the partial derivative of x minus z with respect to x, which is 1, minus the partial derivative of negative y plus z with respect to y, which is negative 1. And we're multiplying this by k. So what we see is that we have negative 1 plus 1i, so we have 0i, minus 1 minus 1, so we have a minus 0j or plus 0j. And then we have plus 1 minus the negative 1k, so plus 2k. So now that we found the curl, all that we need to do is we need to find this normal vector n. So I left a little space up here when I wrote down the surface. Since the surface is already given to us as z is equal to 9 minus x squared minus y squared, we can go ahead and we can actually call this g of xy. And the reason that we want to do that is because now, when we're finding n, we know that n is going to be equal to negative the partial derivative of g with respect to x times I minus the partial derivative of g with respect to y times j plus k. So our normal vector, if I go ahead and write that out, we're going to have our normal vector, well, the partial derivative of g with respect to x is going to be negative 2x. So if we make that negative, we'll have a 2xi. The partial derivative of g with respect to y is a negative 2y. But since we're subtracting it, we're going to be adding 2y times j. And finally, we're just adding k. So now we know what the curl of f is, and we know what this normal vector is, so we can go ahead and use Stokes' theorem. So this is going to be the double integral over our surface S. We know that the curl of f was given by 0i plus 0j plus 2k. And this vector n was given by 2xi plus 2yj plus k. So now that we have this set up, all we have to do is figure out how we're going to integrate over the surface S, and we have to find this dot product. Well, looking back about our surface S, we see that in the xy plane, this is really just going to be a circle of radius 3. So that's going to help us here, and then finding this dot product is pretty simple. So let's go ahead and let's leave this as a double integral for now, but I'm not going to write any of the limits of integration. And this dot product, we're going to have 0 plus 0 plus 2. So we'll have 2. And now we'll go back and we'll look at this. So notice that I said this is going to be a circle in the plane. So here, our ds is going to be given in polar form. So we're going to want to integrate with respect to r and theta. So we'll have an r dr d theta. And r, in this case, is going to vary from 0 to 3, since we have a circle of radius 3. And theta is going to vary from 0 to 2 pi. So now, this is a pretty simple integral to perform. So if you work through this, what you'll find is that this is equal to 18 pi. So now that we found this integral using Stokes' theorem, we'll want to find the same integral using our ideas from line integrals. And we'll want to show that this is equal to 18 pi. So the first thing we're going to want to do when using these ideas from line integrals is reparameterize this curve C. So looking at the surface, we know that the surface in the xy plane is just a circle of radius 3. So we can reparameterize this curve C by writing r of t is equal to 3 cosine of t times I plus 3 sine of t times j plus 0k. So now we have r of t, our reparameterized curve. Here we can go ahead and we can actually find r prime of t, so the derivative of r of t. And we know that this is going to be equal to negative 3 sine of t times I plus 3 cosine of t times j plus 0k. Now the next thing we'll want to do is we'll want to find our f of x of t, y of t, and z of t. And this just comes from knowing what the function f is. And we know that x of t is going to be given by 3 cosine of t, y of t is given by 3 sine of t, and z of t is going to be given by 0. So let's go ahead and let's write down what f of x of t, y of t, and z of t is equal to. So for this, I'm going to come down below it and write what it's equal to. All right, so we're coming up here. We know that y of t is 3 sine of t. So we're going to have negative 3 sine of t plus 0 times I. So we'll have negative 3 sine of t times I plus, we know that x is 3 cosine of t and z is 0. So we'll have plus 3 cosine of t times j. And here we know that x was cosine and y was sine. So this is, we know that x was 3 cosine and y was 3 sine. So we're going to have plus 3 cosine of t minus 3 sine of t. And this is going to be multiplied by k. So now we just have to come back to our line integral, and we have to evaluate the integral of the product of r prime of t, or the dot product of r prime of t, and this f of x of t, y of t, z of t. Okay. So let's leave this as an integral from a to b. Here, let's just write out the dot product. So we'll have negative 3 sine of t times negative 3 sine of t, which is going to be 9 sine squared of t, plus we're going to have 3 cosine of t times 3 cosine of t, which is going to be 9 cosine squared of t. And finally, we're going to have 0 times 3 cosine of t minus 3 sine of t, which is 0. And we're integrating with respect to t. Now, the very last thing that we need to notice is that when we reparameterize this, we parameterized it as a circle of radius 3 in the xy plane. So we want to integrate from t equals 0 to t equals 2 pi. So what we have is this is equal to the integral from 0 to 2 pi. And here we have 9 sine squared of t plus 9 cosine squared of t, which we know is equal to 9. So we can evaluate this pretty quickly. We know that this is going to be 9t evaluated from 0 to 2 pi, which is equal to 18 pi. So since this integral was equal to 18 pi when we used Stokes' theorem, and was equal to 18 pi when we used these ideas from line integrals, we've now verified Stokes' theorem. Thank you.